IB1, IB2, this will be say IB3, IB4, and if we operate this one, this one, DC is set. So if you move, if you here, there will be one beta. If you here, there will be another beta or something like that, right? So your beta can be changed depending on the value of your different IB. So what I want to tell you that we need another supply, and that means we need IB based current. And they mentioned in the video that if you want to operate our transistor, this you can BJT as a switching device for the high voltage DC transmission, HVDC. The example is HVDC. So there will be a lot of power losses because of this conversion also. And not only that, the AC transmission, the grid, so you are connecting like this, the grid, three-phase line, long distance three-phase line. They mentioned that there will be a lot of losses. What are the sources of losses in the transmission line?
Sir, mainly the resistance of the wires.
Okay, so but if you go for the high voltage DC transmission, it is AC.
Sir, for AC, for same wire, for AC, the effective path is smaller than DC.
Yeah.
So
this is skin effect, right?
skin effect, yes, sir.
Yeah, because of the frequency and the current moves to the surface of the conductor. So to transmit the say big amount of current, and high voltage DC transmission line is what is that? Not the light wire, less cross-sectional area wire than the AC transmission. Also, you know that you have already studied the transmission and distribution. There should be a subject T and D. Did you do this T and D, transmission and distribution? We had this subject in our undergraduate. I don't know whether you have learned it. Or there are some capacitance effect, capacity effect between phases and also inductive effect, and that creates a lot of instability. So to avoid this, we can use this high voltage DC transmission. So in the video, it is clearly mentioned that you have to transfer this thing. So suppose this is your generating station. You have the three phase. Then you can step up. Then you must have that three phase AC to DC converter, and then you have DC line. Although they have shown in two wires, but you can use one wire. Another wire can be avoided using the ground. Okay, and this is your DC to AC again, inverter. This is a rectifier, and from there you can go to the distribution line. So this rectifier, that is they are suggesting that not the uncontrolled rectifier we have so far studied, right? In the uncontrolled rectifiers, what are the devices we have used?
Diode.
Diode, right? Suppose this is a single phase two-wave rectifier, and this one is a VDC. IDC. So this is DT. This is D1, this is D2, this is D3, and this is D4. So if it is Vs equal to root 2 Vs sine of omega t, then this Vs is the RMS value. So what is the VDC or average voltage? That should be there. For this full wave bridge rectifier in terms of RMS value. If we have that. If we have this output voltage like this. See, what will be the, if the maximum value will be equal to root 2 Vs, and what will be the VDC in terms of Vs?
0.9.
0.9 Vs, right? Look here, we don't have any control. So this VDC is fully dependent on the magnitude of your input voltage. If it fluctuates, then of course your this DC voltage will fluctuate. That is why we need some control mechanism so that we can have the feedback, and then we can have the control to change the DC voltage according to our demand, so that we always get a constant DC voltage in the power line. That is why we need a controlled, instead of uncontrolled rectifier, we need a controlled rectifiers. So the controlled rectifiers, we shall use thyristors. Introduction is okay? Introduction is okay?
Yes.
Yes, sir.
Now, let me stop share this one. I want to show the book. So this is from the chapter 6 of your Net Mohan book. Net Mohan. We are using the 3rd edition, right? So this in your PDF file, this chapter 6 has come after chapters, actually 5, chapter 5, then chapter 7, then the chapter 6 is there. So don't worry, when you will check, it will come after chapter 7. You understand what I say? In your PDF file. PDF file that has been, did I give you the PDF file?
No,
Hello?
sir.
No? Okay. So did you get the PDF file?
Sir, I had it from my BSc years, although that is the 2nd edition.
Okay, so I can always give you this one, no problem. I can give you this one to your WhatsApp. This book. I will give you. You have maybe this side I can put it in your WhatsApp. Okay. So now this is the 3rd edition. So chapter 6, you mentioned that line frequency phase control rectifiers and inverters. So line frequency AC. Your AC control DC. Output will be controlled. VDC will be VS. Of course, there will be VS and then function of some parameters. That parameters can be controlled so that the VDC can be controlled. We will learn this. But the very interesting thing is that look here that the arrowhead has 2 ways. So you can make AC to DC. You can also convert the DC to AC. That means from the DC side or the load side, you can always feedback the power to the input side. And if you do that, then it will be known as the inversion mode of operation. Sometimes people call inverters. Actually, inverters normally we know that which convert DC to AC. We'll learn it at the end of this, maybe last few classes, 1 or 2 classes, we shall introduce the inverter. You know that inverter, right? In the undergraduate, you have already learned. Okay. So let us go to the introduction thing. Each article has an introduction, and the conclusion is very important. When you write even a paper, you have to be very much careful about to read the introduction or abstract, all those things. So in chapter 5, we have discussed the line frequency diode rectifiers that are increasingly being used at the front end of the switch mode for electronic systems to convert the line frequency AC input to an uncontrolled DC output voltage. If you use the diode, then it will be uncontrolled. However, in such applications such as battery charger, a class of DC and AC motor drives. So in the battery charger, also in the DC motor drives, where you may want to control the speed of the motor, where you need a variable DC supply, and also AC drives, AC motor drives, where DC voltage will be converted to AC, and then from that you can use motor, AC motor also. So if you change this DC, then the magnitude of the AC will be changed, and the motor speed will be also changed. So they mentioned that for the battery charger as well as for the AC or DC drives, it is necessary for the DC voltage to be controlled. And also high voltage DC transmission, we have already seen that you need that AC to DC converter or DC to AC converter. The AC to control DC conversion is accomplished in the line frequency phase control converter. What does it mean by phase control? Actually, the input voltage will have the wave shape like this. Then we may get, okay, for the half wave rectifier, we will get this one, right? If you use the diode rectifier. But if you want to control it, you may get a voltage, output voltage like this. You may omit this portion. So omega T, and this is omega T. So this is pi, this is twice pi. So this is for the uncontrolled rectifier. You may control the output voltage like this. You may not want this portion. You can control the phase. That phase will be from the control of this one from your 0 to pi. You can move here. You can omit this portion. You can get, you may want to get, and if you take the average value, of course, this average value will be less than the average value of this one. I am talking about the half wave rectifier. You understand what I want to say?
Yes, sir.
Okay. And other people, Nadim, other students.
Yes, sir. I'm
Yes, sir.
Okay, very easy. So that is why it is known as the phase control rectifier, phase control converter. By means of how will be that we use the thyristor. In the past, these converters are used in the large number of applications controlling the flow of electric flow. When the increasing availability of the better controllable switches in high voltage and current ratings, new use of this thyristor converter nowadays is primarily in the 3-phase. Actually, now a lot of good switches are available, so people are using this one for the high power conversion. These thyristors are used for the high power conversion. And 3-phase. Anyway, if we're going to the 3-phase, we must know the operating principle in the single phase. This particularly true, this This is particularly true in application most of the high power level where it is necessary or desirable to be able to control the power flow in the both direction, the AC to DC side. That means so AC can be converted to DC or DC can be again converted to AC. Example of such application converters in the high voltage DC power transmission that is given of this book in chapter 7. We shall not go to that application. It is your duty to do that. And for the those who are interested, for the drives, motor drives, AC motor drives with regenerative capability that has been given in chapter 5. Okay. Now, as the name of this converter implies, the line frequency voltage are present on their AC side. In this converter, the instant at which the thyristor begins or ceases to conduct depends on the line frequency of the AC voltage. Of course, frequency. So in the video, it is mentioned that how you want to stop conducting the thyristors. They mentioned that you can use an LC oscillator in conjunction with the DC, and if you add this AC with this DC, and if this LC peak value is greater than the DC voltage you have applied to the thyristor, and in the reverse bias when since the LC oscillating AC has a peak value greater than your DC, then you will have a reverse bias. And with that reverse bias, if you have a zero current, then the device will automatically stop. You understand what I say? No or yes?
Yes, sir.
Suppose you have a DC and you have a thyristor like this. Thyristor this is your anode, this is your cathode, and this is your gate. You know all these things, right? With your postgraduate students. Now, if you apply the gate current here, then the thyristor will be turned on and turn on forever. You know it, right? Am I correct or not? If this is your, suppose we have applied a gate current here, so T1, then up to this there will be no voltage. This will be the output voltage V0. And after that, it will be same as your E. You understand what I say?
Yes, sir.
So how to stop this conduction? Suppose if you can somehow put a AC oscillator here, and then if this combined voltage in the positive half cycle, of course it is positive, in the negative half cycle, suppose this is your 10 volt and suppose this is your 15 volt, in the peak value is 15 volt, and in the negative half cycle, the effective value will be -5 volt, and that -5 volt is reverse bias this thyristor, and if the current is 0, then it will stop conducting. You got the idea?
Yes, sir.
It should be noted that the uncontrollable line frequency dial rectifier of the chapter 5 are subset of the control rectifier. Actually, control rectifier of the main thing. Why it is mentioning that it is subset? Can anyone tell me? Suppose you have an AC supply, and you have a thyristor here. Suppose this is the resistance here. So the input voltage is like this. I want to make, okay, if you replace this one as a diode, then what will be the output voltage? We'll get like this, right? If this thyristor is replaced by diode, that means here.
I think they are called a subset because if we always fire our thyristor at 0 degree, it will.
Yes, you are correct. If the firing angle is alpha equal to 0, then we will get this half wave rectifier, right? Am I correct or not? you are firing at omega t equal to 0. Then you will get that half wave. And then if it is a resistive load, then the current will be like this. And if the current is 0 and then negative voltage has come into the picture, and this thyristor will be reverse bias and current is 0, so it will stop conducting. I told you to stop conducting any electronic devices, which must be reverse bias as well as the current through it must be equal to 0. Okay. The reasons for discussing the diode rectifier separately in the file have to do with their increasing importance and the way in which the DC current flows through them. In chapter 5, it was pointed out that in many application line frequency diode rectifiers, the current ID through them does not flow continuously due to capacitor filter for some smoothing the DC side voltage. Therefore, the emphasis in chapter 5 was on the discontinuous current conduction mode. So we did not, yes, we have already discussed about the discontinuous mode of operation in the diode rectifier, if you remember all this. So you better you read this introduction and try to understand what they are trying to say. Now we want to discuss something about that figure 6.1. So this 6.1a, look here, this is your AC side. This could be single phase or three phase, 50 or 60 hertz. And that this one will be the DC side. And this is the symbol of thyristor rectifier or control rectifier. And now we have here, they have plotted, this is your ID. Suppose this is the DC ID. And this will be the VD. So it is possible the current will be always flow from positive to negative. Current will be always positive. Okay, the current will be positive, and it has a limit maybe. And but voltage can be made either positive, this is your positive, and you can make it negative. We shall come how to do that. Probably you have already seen that one, right? If you use the highly inductive load, you may get a negative output voltage. We will come back inshallah. So like then the PD will be your VD multiplied by ID. So in this coordinate, if in this coordinate ID is positive or negative? Zero, and this is a positive, right? So ID is positive or negative in the first coordinate?
Positive. Positive, sir.
Positive. And VD?
Positive.
VD positive. So your PD is positive. So if source on this region will be rectification or it will be absorbing the power. But in this fourth coordinate, PD will be, ID is positive, but VD is negative. Am I correct or not? Look here, VD is negative. So PD is negative, right? Power is negative. So in any application, if the power is negative, it means that it is pushing back the power to your input side. So this is your inversion operation. So look, they have mentioned that limited by the component's current. That means the maximum current that will be limited by the, you will use the thyristors or any other devices. It is the current limitation, and limited this one, the highest value will be limited by the input voltage, maximum input voltage that can be there, right? So if alpha equal to 0 for the full wave rectifier, what will be your output voltage? 0.9 Vs, right? And that Vs is limited. That has come from the input voltage. So this Vs is limiting the highest value of your VD. You got my point?
Yes, sir.
Yes or no? If alpha equal to 0. Okay. Now in our diode cases, we have studied three basic circuits, if you remember. One is with the resistive load, another is the RL load, another is the L, and with a constant DC source.
Yes,
Can-
sir.
can you
One, sir. So the inversion will never happen with the regular diode, sir. It's right, sir. It's only the thyristors thing.
In the regular diode, yes, no. In the regular diode, it is not possible. Because you are getting, in the diode, you are getting always the full wave, right? But in the, okay, we'll come back when we'll use the thyristors. If your alpha equal to greater than 90 degree, then you will see that for the highly inductive load, you will get the negative volt. There, the output voltage will have a negative component that will be greater than the positive component. We'll study this one, inshallah.
Okay.
Okay.
Yes.
So, okay, let us try to understand the basic circuits. This is your thyristor with resistive. This is half wave or full wave?
Halfway.
Okay. And also in the diode case, we have studied with the half wave. If we have that concept, then of course, inshallah, we'll go for the three phase and also the full bridge rectifier. So this figure is very clear to you if you look at the figure. So you follow my pen. So this is what?
Source.
This is what? Source. Good. This is your source. Look here, they mentioned that this is the source voltage. Okay, now half wave rectifier for the positive half cycle, that this thyristor is forward biased or reverse biased?
Forward biased.
Forward biased.
Okay, so to turn on any electronic device or electronic device, it must be forward biased. We have there are two conditions to turn on the thyristor. One is that you must have the forward bias voltage, and then you must have that
Positive current flowing.
gate pulse. Otherwise, you know that in the video it is mentioned that by applying. Okay, let me. Actually, I want to skip because this is the undergraduate level. I teach very minutely, but I thought you understand these things. So this is the PNPN. This is your anode and this is your cathode. And now if we apply a positive anode to cathode voltage is positive, this junction is forward bias, this junction is also forward bias, right? But this junction is reverse bias. Am I correct or not? In the
Yes,
video,
sir.
it is also mentioned. So if we go to the IV characteristics, your IA, your thyristor here. Suppose this is your IA and this is your VA. If we apply a positive voltage, which is forward bias, but this junction is forward bias, this junction is forward bias, but this junction is becoming more and more reverse bias, right? So there should not be eventually any current would be zero through your thyristors. Why?
Because
Why?
J2 is reverse biased, sir.
Yes, J2 is reverse bias. So, but if we increase more and more, eventually there will be a breakdown, and that breakdown is known as the avalanche breakdown or the Zener breakdown. But we don't want to operate our transistor in the breakdown. We want that you have already learned the control characteristics or the switching characteristics of the device, that we want to block the voltage if you want to control it. If it is operating with high voltage, then you will lose the control, right? You got my point or not? Suppose I'm not good at drawing. So there is a block. The water is accumulated here, here, and there is a little hole here. But we can control the width of the hole. If we make it very tiny, a small amount of water will come here. If you want, we can make it large, then big amount of water will flow like this, right? So that is our, this is, suppose this is a valve. So if we have that control, then we can control the flow of the water. You understand what I say? But if the water is accumulated, and if it is overflow, then you will lose the control. So that is your breakdown. We don't want that the breakdown operation will occur in the diode case or the thyristors case. You got my example, what I want to say?
Yes, sir.
So now, if, suppose we are increasing the voltage, input voltage, and then we have applied a gate pulse here, IZ, and then this junction will be broken down. Actually, they have told that they will supply a lot of, this is PN, this is P and N, but they will supply a lot of electrons. Eventually, all these three, 1, 2, 3 layers will become the PN. N, this will be N. So we have the PN junction characteristics, like the diode characteristics, if we apply a gate pulse like this. So we have applied, say, suppose we have applied a certain amount of voltage here. This voltage we have applied, and then we have applied IZ, the firing pulse, or sometimes people call it gate pulse. And then the junction will be broken down, and this will simply work as a diode. Although I am showing you the characteristics like this, but practically, it will be, but ideally we can just as a constant voltage diode model. We have the constant voltage diode model. I have taught this one in your second semester, those who have come from the IUT. Can you remember? Hello, diode. Can you remember this one?
Yes,
like
sir.
This is your VD and this is your ID, constant volt, and this is your 0.07 or 0.06.
Yes,
So
sir.
here
I
also-
have that characteristics.
Okay, good. So in the thyristor, actually, there must be a current. This current will be known as latching current. You must have this current, otherwise thyristor will not start conducting. We call it latching current. Okay, if you cross that latching current, then the thyristor will be conducting. And if your EAK voltage is positive, that means sufficiently forward bias, then it will continue to conduct. But if you want to stop conducting the thyristor, then you must go back to a current that is known as holding current. Have you heard the name of this holding current and latching current? If this current falls below a certain point, then the thyristor will go. Automatically, the current will fall to 0, and the thyristor will be treated as open switch or off switch. Have you heard the name of latching current and holding current?
Yes, sir.
Yes, sir.
Where did you? I did not teach you in the power electronic course of the undergraduate level.
Sir, I think you did in thyristor.
Okay.
Sir, we also
Good.
did hardware experiments on this.
Yes.
Yeah. Okay. Good. So you are much more smarter than me. Okay. Let us now see for the basic circuit. So this is the half wave rectifier, and for this one is the positive half cycle. The thyristor is forward bias, and until alpha we did not apply any pulse. So the thyristor is the junction 2. The middle junction is reverse bias, and there will be no flow of current. And then at omega t equal to alpha, then we have applied the gate pulse like this. So practical gate pulse will looking like this, but you will see that in the different books, the gate pulse will be like this. Actually, it will never go immediately to a certain point, and it never comes at 0 time to 0. Actually, the pulse will be like this. If you make a firing pulse circuit, you will see that the pulse will be like this. It takes some time, and also it takes some time to hold down. Single shoot generator circuit, by using the op amp, you can always build up this kind of circuit. Okay. Anyway, so we have applied this gate current, and it is not continuous. Look here, it is not continuous current. What is the problem of giving the continuous current?
Power loss.
Yes, power loss. What is the point if only a single pulse is enough? So we don't need to give this thing, but we may need to give, if the LC circuit, we may need to give train of pulses. Can you remember in the undergraduate level we have learned it in the AC controller? Can you remember train of pulses we have applied? Because if the current is not 0 before in the previous cycle, then if you apply the gate pulse, although you may have made the thyristor forward bias, if the current is not 0, then you cannot apply the second pulse. That is why we apply the train of pulses. Can you remember under postgraduate students in the I don't know, 11th chapter 11 of the Harvard Rashid's? I forgot.
Sir, please, can you briefly explain again, sir?
I don't want to explain it. Just this one. Can you remember this? We have used this kind of things. This is your Can you remember this? Suppose this is your T1 and this is your T2, and then the positive half cycle, the current will still be going on there. And then then the negative half cycle, if we apply the another pulse now, gate pulse here, the current is not still 0, but although the voltage is 0, but current is still there. If you want to apply the gate pulse, then you will lose the control. Then what we do, we give this kind of train of pulses. AC controller, in the AC controller circuit. Can you remember?
Yes, sir.
Hello?
Yes. Now I can remember, sir.
Sabik is sleeping.
No, sir, I'm here.
And other people, Ashraful. And I'm very sorry, I cannot remember the other people from the other university. I am very bad remembering the name of the people, but since they are the teachers, so I can remember their names. And also Ashraful, since it is my name, I can Ashraful Islam Bridha, and other people are there. And also we have some students from the other universities. So you want did you do that thing from the other universities? This train of pulses we have to give if the load is inductive for the AC controller circuit. Can you remember it? Hello. Hello. I'm asking the student from the other university.
Yes, sir.
If you did not, so you go to the Harun Rashid's books for the AC controller or AC regulator. You will see it. Okay. Anyway, so here we have applied the single pulse here. and this thyristor is already forward biased, and then the current will start flowing, and the current will have the same wave shape of the voltage with the resistive load used here, right? And it will have the peak value when the voltage will have the peak value at pi by 2. And the current will be 0 at omega t equal to pi, since it is resistive load, and voltage is 0, that is why it is 0. Now, after omega t equal to pi, the voltage is negative, right? So what will be the biasing condition of your thyristor then with this negative?
So reverse bias.
Reverse biased.
It is reverse bias. And also if you even apply any gate pulse here, nothing will work. So this thyristor will be turned off for the, since we got already the 0 current and also reverse bias. So I told you to turn off any power electronic device, the current should be equal to 0 and the voltage is also reverse bias. So the thyristor will stop conducting between, for the resistive case, omega pi to twice pi. That means this. So there will be no current. Current will be 0. If the current will be 0, means this thyristor is open. So and also the voltage will be, VD will be say IR. So I equal to 0. So VD will be 0. So you will get the 0 voltage. And you should get the 0 voltage also between 0 to alpha. Right or wrong? Because we have not applied any gate pulse between 0 to alpha. Okay, so when we have applied the gate pulse for when the voltage is positive, so the thyristor is forward biased, also on. If it is on, then your VD must be equal to your VS, right? Kirchhoff voltage law. Negative positive VS, positive negative VD. So VD must be equal to VS. So we see that it will follow the VS. And after that, pi to twice pi, the current is 0 and we should get it. You understand it or not? Any
Yes, sir.
problem? Any problem to understand it? So now, if I plot separately the VD, if it is alpha, so our output voltage will have the wave shape like this. 0.5. I want to find out the VDC or average value. Oh, or V average. How can we find out the average value? How can we find?
So integrating the voltage from alpha to pi.
Why? We must get that area, right?
Yes, sir.
And then we have to divide it by twice pi.
Yes, sir.
And that will be, so area will be nothing but the integration alpha to pi and root 2 Vs sine of omega t, d of omega t, and then we have to divide by twice pi. If you complete the integration, then you will get root 2 Vs by twice pi, and then 1 plus cosine of alpha. So now we got the control parameters. What is the control parameters? Controlling parameter. If your alpha equal to 0, if you apply the gate pulse here, then if the alpha equal to 0, root 2 Vs twice pi, then multiplied by 2, 2 to cancel, so root 2 Vs by pi, that should be your 0.5 Vs, right? So your output voltage wave shape will be just a diode rectifier. Yes or not?
Yes.
Hello? Now, if you increase the alpha, suppose you are increasing the alpha, so this is the highest value, right? highest value of the VDC will occur if you apply the get pulse at omega t equal to 0, alpha equal to 0. And then you, if suppose your say alpha equal to 90 degree, then your VDC will be root 2 Vs twice by then 1 minus cosine of 90 degree, it is 0. And then you are getting root 2 Vs by twice by, and you are getting 0.45 by 2 Vs, 50% of the diode rectifier voltage. You understand it?
Yes, sir.
So this is the wave. Then if you can always generate a pulse generating circuits, and you have to synchronize with the input voltage, then you can vary the alpha from 0 to pi. So your this is the phase control. The term phase control rectifier is like that. You can have the control parameters that will vary from 0 to pi. Everyone got it?
Yes, sir.
I want to hear from other people too.
Yes.
So
Yes,
we
sir.
have 20 students. So 80 students have already withdrawn, have left. So we have the now 20 students today. Before that break, we had 24 or 25 students, right? Hey, Abu Bakr.
Yes, sir, I'm here.
So your international students, are
Yes.
they still in this course, or they have left? You don't know.
I think Aldi and Sunnat already took power electronics in master, so they don't take this course. Yes.
Now, we shall now discuss about the RL circuit, right? So, did you not discuss the RL circuit for the diode case?
So you did.
Okay, here, I don't like this figure. Let me draw by myself. This will be your input voltage was by T, and we have applied a gate signal here. Yes, alpha. So this is the RL circuit. So of course, you see, the current will not be sinusoidal rather than different. If you when the diode is conducting, then if you apply the partial voltage, the Ri, then L di by dt, and then we have to solve this. This will be your root 2 V sine of omega t, and then if you do the differential equation solution, then we will have the expression of I. Okay, forget about the expression. Let us try to understand what will be the wave shape of the current arbitrarily. Okay. Okay, let us first try to draw the say VR. This will be VR, right? That is your I multiplied by R. Look here. So if this is VR, and look here, and the peak value of the VR is this point. Is the peak value. Okay, let us put this as theta P. And what will be the wave shape of the current? Will it not be the same as VR?
Yes, sir.
Okay, let us try to plot this one too. This is the red one is the current wave shape. and it will have the peak value at theta P2. So like we have already discussed this kind of thing. Vs will be your VR plus VL. And when at the crossing point, Vs equal to VR, crossing point. So VL equal to 0. VL equal to L di by dt equal to 0. So di by dt will be 0 at the peak value of the current. Am I correct or not? Di by dt will be 0 at the peak value of the current, maximum. We discussed these things for the diode case also. Right or wrong? Hello? The peak value of the, can you listen to me? No sound.
Yes,
The
sir,
peak
right.
value- Yeah, peak value of the current will occur at the crossing point of Vs and VR. Why? Because at the crossing point, Vs and VR will be equal, and if you substitute this equation, then we see that VL equal to 0. VL is nothing but L di by dt equal to 0. So L cannot be 0. It is a finite value. So di by dt will be 0. Di by dt will be only 0 when there will be no change of the current slope, and it will be the peak value. Okay.
Yes, sir.
Then, like what we did for our previous, for the diode case, if we want to plot the VL, so VL will be up to this, the di by dt is positive. So we'll get that positive VL. And then after that, after this theta P, we see that this slope is negative, and we get that negative VL. This will be the wave shape of your VL. And this is the area A, this will be area P, of course, this area area B. Okay. And in this book, let me clear out all these things. What they did, so Vs equal to VL plus VR, then VL can also be drawn like Vs minus VR, right? Can I do that? So this is your VR. Can you see, follow my red mark? And
Yes,
this
sir.
is your Vs. So this Vs minus VR will be positive. So that has been shown here. Although I have shown in the different way. And for the after the peak value of the current, this VL will be this one negative. Actually, that is why they have shown this one. You got it or not? But if you don't understand these things, so forget it. The way I have shown you, the VL will have the wave shape like this, and then it will be like this. This is VL. Okay? But they have plotted this one by following this equation. I don't like this. Okay. Then let us see. So that has been finished. And then now we shall look at the third figure. What type of load we have used here?
Resistive.
This one. This one. We did that for the diode case. Then suppose it is like a DC motor with the armature resistance of 0, and this ED represents the back EMF, and L is what? L is what? Armature inductance. Okay. So here, okay, we have applied the get pulse. Okay. First, let us see. So what is this? What is this line?
Sir,
You were
ED.
Yeah, you were sleeping actually. Okay. So we want to apply the gate pulse. If we want to, okay, like this VS, right? This VS is less than your ED. This VS is less than ED until theta 1. Now, if anyone wants to apply any gate pulse here, will this thyristor conduct?
No, sir.
No, sir.
It's not forward biased yet.
Yes, right. So forward bias is starting from after omega t is equal to theta 1. So you can apply after. So they have applied at theta 2. They have applied this one, okay? And then, so since there was no current before that theta 2, suppose this is also our alpha. So the output voltage, so no drop here, V must be equal to ET, so you will get the output voltage will be ED. You got it? You got it? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Okay, then you have applied the gate pulse here, because also already your VS is greater than your ED. So this diode is short circuited, and this VD is VS. So is VS. And also the same reason, the current will have the peak value at the crossing of your at the VD, ED and VS, because VS equal to VL plus ED. So when VS equal to ED at the crossing point, then your VL equal to 0. If VL equal to 0, of course the current will have the peak value. The same thing we have done, right, in the earlier case. But current is not 0 at omega t equal to pi. Look here. Why? Because the inductance will store some energy and it will take some time. Although the voltage has gone to negative reverse bias, but since there is no path to follow the current, so current will still conducting unless all the total energy will be dissipated in some cases. There must be some resistance here, or the battery charger will absorb this one, and then current will go, and current will stop conducting here. So until this, when the current will be conducting, that means thyristor is shorted and it must follow the VD must be equal to VS. So VD is equal to VS. Even in the negative, we got it, right? And then when the current is 0 and voltage is reverse bias here, so what will happen to your thyristor after theta 4?
So it will turn off.
It will turn up. Current is 0, the voltage is negative, so it will turn up. If it is turn up, then and we can always go back to the right side and see your V, that means output voltage must be equal to again ED, and it will continue to do that, and it will halfway rectify. In the negative side, of course, will not the thyristor will not be turned on, and it will continue to ED, and then again, if you apply another gate pulse here for the next cycle, this is your twice pi plus theta 2, then you will get that. You understand the whole concept? We did the same thing in the diode case. Hello?
Yes, yes, sir.
Yes, sir.
Okay. So good. And next figure, they have plotted the here. You should see. What is this? What are these things? What is this?
Thyristor voltage.
Yes, voltage across your thyristor. So when the thyristor was not conducting, okay, up until this one, we see that if you apply the Kirchhoff voltage law, then the negative, this is a positive. Okay, let us apply the Kirchhoff voltage law. Negative positive PS, then positive to negative minus V thyristor. Okay, and then what is that? It is open, right? Sorry, it is open, so there will be no current here, and then positive to negative minus ED equal to 0. So V thyristor will be your Vs minus Ed. So this Vs is less than your Ed. So that is why you are getting negative voltage. And that's exactly this point, Vs and Ed equal, right? Am I correct or not? At theta 1? At the theta 1, Vd and Vs equal, right?
Yes, sir.
So that is why you will get the 0 voltage, Vs and Vd equal 0 voltage, and then after that Vs is equal to greater than your Ed, we are getting the positive voltage. And then after theta 2, the thyristor is on. So what should be the voltage across your thyristor when it is on? Ideally,
0.
because you are getting the 0 voltage here. And after that, again the thyristor is off. Then you have to apply the Kirchhoff voltage law. Now the voltage is negative, minus Vs minus Ed at the peak value of the negative peak value of your Vs. So that is this one. And what? Tell me what is this voltage? Minus root 2
Yes.
Vs or Vn minus Ed, right?
Yes.
So this will be the peak inverse voltage across your thyristors. You understand? Hello.
Yes, sir.
Hey, Abu Bakr.
I'm listening.
Abu, you are listening. So are you
Yes, sir.
understanding? Are you understanding?
Kichu Kichu, yes.
Yes, good. So these are the things they have mentioned, and with that one, they also find out with the, how you will get the expression of I. Then you have to integrate it, like for the inductor plus constant voltage. So you can. Should I continue or I should stop here?
I think for today's okay, sir.
Okay, let me show you how to generate the get pulse. Okay,
Okay, sir.
just and after that I will finish. Today I feel better. My physically I am okay. I thought I am dying. I got the corona and I am dying. Those who are my Facebook friend, you have probably seen my status, right? And some of the
No,
Yes, sir.
I travel. I didn't see anything. I didn't hear about your corona thing, sir.
No, I did not
Oh.
have the corona, but the symptoms of corona.
Oh, subhanallah.
Okay.
Now you are feeling better.
Yeah, alhamdulillah, it is more than 14 days or 15 days. I'm feeling
Oh,
better. It's still
mashallah.
little weak, but okay. And that is why I did not go to IT on the Eid day. You
Oh,
understand?
yes.
I did not go. Okay. So how to generate this get pulse, and that will vary from the 0 to pi. So you must have that input voltage synchronized with your to generate the. But if you don't know the phase of your input voltage, you cannot control, right? You must know where are you. Are you here? Are you here? Or are you here? Or here? So that is why you must take that input voltage that you want to control, and then you can use a transformer, and then you got the synchronized voltage. This is the synchronized voltage. This one, sinusoid. And use a sawtooth generator. When the voltage is there, you will get one sawtooth, and also in the negative, you will get another sawtooth, and also in the positive, you will get another sawtooth. So sawtooth generator, you can use op-amp to generate this one. Then you have the sawtooth, this one, and you must have a control voltage, maybe a DC voltage here, and then you compare. So you can move this control voltage. Look here, this control voltage, you can move here, or you can come back here. So, okay, when suppose you are at the peak, so if it touches here, so you may get a get pulse. Where you are touching, you will get that get pulse. Okay, let me go down. Otherwise, you will not understand this. Here. So look here. This is the crossing of your control voltage and sawtooth, and there is a get single shoot generator. It is available in the market, and also you can build up. So when this comparator circuit, your control voltage and sawtooth voltage crosses each other, then you will get a pulse. And you can, okay, if you want to use the negative one, you can always get another pulse. But here, since we are talking about only the positive, so they are showing you that only this one. So now, if you move this control voltage here, look here, your pulse has alpha to new value of alpha 1. You understand it or not? Hello?
Yes, sir.
Yes, sir.
And if you go to the peak value of your sawtooth, then what will be the value of your alpha?
Pi, sir.
Pi. So you can vary your this get pulse from 0 to pi. If you are here, just touches here, you will get the get pulse here. If you are say in the middle, your alpha will be 90 degree. If you are at the peak, then your alpha will be a pi, omega t equal to pi. So you can always generate. So if the university would have opened, then I could have told you to build up a pulse generator circuit and show it to me. That will be your project. I can add some marks for this. So since we are at the pandemic, so we cannot do it. So okay, that will be the end today. And then we shall start our circuit, inshallah. This is the practical converter with the LS, and this is the 3-phase. And then inshallah we shall start with this one, the single phase bridge rectifier in the next class. Okay.
Yes, sir.
How many students? Okay, let me then find out who are not there. But I'll check that the people who are not here in my report list, I could have found the people. So everyone got the student ID. So Sabik has sent me the list, right?
Yes, sir. But maybe some students have updated student IDs. I'm not sure. That was, sir, that was when I had the information. I sent a message in WhatsApp, and the people that sent me the student ID, I added to the list.
So did you send it to my email?
Yes, sir.
Okay, I'll check.
Should I send
Okay.
again?
Now, okay, you can, if you want.
Okay, sir.
20 students. So in the first class, we got 29 students. So 9 students is missing, whether they will join it or not. I'll be very glad if the students will be less, because then I'll need to mark less scripts, and I need to take 5 less students. I need to take the project less student. Okay. Okay. Thank you very much. You can leave, no problem.
Okay. Thank you, sir. Have a nice weekend.